All right, so here we have a car that starts from rest and it accelerates along a straight track. It said it accelerates at a rate of 10 meters per second square for the first 10 seconds, and then it decelerates at 2 meters per second square till whatever time here. Okay, so here's the graph. It says the acceleration for the first 10 seconds is 10 meters per second square, as shown in that blue line. And then a phenomenon occur here where it starts to decelerate. All right, let's go ahead and crack out A, B, C, and D. Part A asks us to find the change in velocity during the first 10 seconds. So really it's just from 0 to 10. So where this is right here, okay, which is looking at the first half of the graph here. All right, to find change in velocity, I'm just going to say acceleration is change in velocity over change in time. Well, in order to get delta V by itself, I need to multiply both sides by delta T. Or you can just move this delta T from the bottom right up to the top left. Continue just multiplying. Alright, other than that, I have delta V by itself now. I can just plug in A and T. A is given as 10 meters per second square, and that's a positive because it's above the T axis, and then T here is just 10 seconds because it's specified from 0 to 10 seconds. So I have 10 meters per second square times 10 seconds. So the answer is going to be plus 100 meters per second, which is the change in velocity. And it says change in velocity, and velocity is a vector. So I'm going to go ahead and include the fact that it's moving to the right. Okay. Why? Because this particular area is moving, or this particular area is positive. Now, on the topic of area, because you're given an acceleration versus time graph, you can actually solve part A using this particular strategy. You can just find the area. Okay. Anytime you're given an acceleration versus time graph, one of the information that you can pull out is the area. The area between the line and the t-axis is your change in velocity. It does not tell you VI, it does not tell you VF, it just tells you what the change is. Okay, so keep that concept in mind. It's not safe to assume VF and VI, it just tells you what the overall change is during a certain time interval. Alright, so I made a note for you here. Delta V is indeed the area, so therefore this is just a 10 by 10 square. So I'm just going to say that the change in velocity here is just times base times height, because this is a rectangle, or or a square. Excuse me, it's 10 by 10. Other than that, if you multiply base is 10, height is 10, 10 times 10 is 100, and once again, I'm just going to include the plus sign because this is average velocity. All right, velocity is a vector. So I'm done with part A. Part B, it says calculate the car's average velocity during the first 10 seconds. To find average velocity, I'm just going to go ahead and say that it is displacement over time. I know what t is. I don't know what delta x is. So I can find delta x pretty quickly. So delta x I can just find using kinematics. Delta x is vi at plus 1 half at squared. Vi is going to be 0 because it says starts at rest. So I'm just going to cancel that term out. Here is just plug and chug. A is 10. T is also 10. Carry the square down. So if you do that correctly, delta x is going to be 500. So I'm just going to carry this function down. So once again, average velocity is delta x over delta t. I know delta x I just found is 500. Delta t is 10 seconds. So we have 500 meters in the numerator, 10 seconds in the denominator. And the answer is going to be plus 50 meters per second. The plus sign is necessary because once again it asks for average velocity. All right. The other way to find it, though, if you like, is to recognize that because acceleration is constant, right? For the first 10 seconds, the acceleration is a constant 10 meters per second square, 10 meters per second square, 10 meters per second square. And because acceleration is constant, you can find average velocity using this particular function in kinematics as well. Here, I know VI is 0 because it starts at rest. And then I can find VF really quick. Okay, VF here is just AT plus VI. Well, VI is 0, A is 10, time is 10. So 10 times 10 is 100. So really, if you think about it, it makes sense. V average now would just be VF, which is just positive 100 because it's accelerating to the right in the diagram, divided by 2. So therefore, 100 divided by 2 will give you also 50 meters per second. But as you can see here, the answer comes out the same, regardless of which strategy you use. Okay. All right, let's go ahead and crack out part C. It says determine the time needed to stop the car. So I think this one's probably the hardest one out of the parts. To find the time needed to stop the car, I'm just going to once again apply my average acceleration equation, and then I'm just going to go ahead and switch A and T. I need to figure out T, so I'm going to get it by itself by multiplying both sides by T, but at the same time divide both sides by A. So I'm going to move delta T up to the top left numerator. I'm going to move A down to the right denominator. So I'm just going to also break up the VF into change in velocity into VF minus VI. Here VI is 0. Okay. Oh, excuse me, VF is 0 because it says determine the time needed to stop the car. If it's going to come to a stop, it implies that the final velocity is 0. But VI here, we already know this though. Okay. The car starts at rest initially, and then it accelerated for a time of 10 seconds at a rate of 10 meters per second squared. So we know our final velocity that we calculated here in part B. Watch what I'm circling. Okay. So after 10 seconds, the car's instantaneous velocity is 100 meters per second. Okay. Therefore, when I'm looking for the time that it takes to stop, the velocity at 10 seconds is now my initial for the remaining time, which I don't know what the time is. So by the time the car gets to this point, it's already moving at 100 meters per second. So I'm just going to go ahead and substitute in VI is 100 meters per second. The negative sign I carry down because that's part of the function. Here, acceleration, though, if you look at the graph correctly, acceleration here is now beneath the t-axis, and it is a constant -2. Okay, so I want to point out in the wording, though, it says decelerate at 2 meters per second squared. So you notice here the negative sign is not given in the statement. However, the graph shows us that decelerating here in this case is negative because the object's moving rightward. Okay, so the negative sign here will cancel out. Therefore, 100 divided by 2 will just give us 50 seconds. Okay, so that would be the time it takes for it to come to a stop. So that's my answer for part C. Now, if you want to, you can think like this. Okay, the change in velocity during the first 10 seconds is positive 100. Well, to get the car to come to a stop, you need another negative 100 because positive 100 and negative 100 will cancel out, which will give us 0, which will put the car back at rest. So you notice here I shaded this area here in purple. I know that this area here in purple must equal to the area here in orange because the change here is positive 100. For it to come back to a stop, the change must also be negative 100. So therefore, I know that this area down here must be equal in magnitude, just opposite in direction. Okay, so hence, that's where the negative 100 comes from. All right, so I can just use the same function here. I can say acceleration is change in velocity over change in time. So, well, to find delta t, I'm going to do switcheroo again. However, you notice here, I want to keep delta v as is though, okay? Because the area beneath an acceleration time graph is your delta v. So here my delta v is going to be negative 100 meters per second. A is -2 because it's over here on the graph. All right, other than that, I'm done. So I'm going to utilize the area with just change in velocity. Therefore, change in velocity is negative 100. It's negative because I need a negative 100 to cancel with positive 100. And then you can see 100 divided by 2 will give you the same time, which is 50 seconds. All right, let's go on to D. D asks you how far it has traveled. So let's go ahead and crack it out. So I can use kinematics, and then I can just do this, okay? I can find the distance it traveled during this 50 seconds because after 10 seconds, the car was already moving at a rate of 100 meters per second. So here, my VI is not 0. My VI is actually 100 because I'm just doing for the second 50 seconds, okay? So here is VI, this is 100. T is 50 seconds because this is how much time it needs to take, how much time you need to bring the car to a stop. Here, acceleration is -2. I want to remind you that the graph itself, is a -2, even though the wording says +2 here, but the term decelerates, it suggests that acceleration is a vector, so it needs to be negative for this particular problem. And here T is 50, and the square got carried down. So if you do this correctly, you should get 5,000 minus 2,500. And then if you simplify that, you should get 2,500. Now, this is just the distance, okay, for bringing the car to a stop. But that's not the answer yet, okay? It says how far has the car traveled? Well, if you pay attention in part B, we know that during the first 10 seconds, where I'm circling back and forth with my cursor, during the first 10 seconds, the car has covered a distance of 500. Well, and then it's going to cover an additional 2,500 meters, okay? So therefore, to find the total distance, I would just add those two values. So 500 here is the first 10 seconds. and then 2,500 years from what is it, 10 to 60 seconds, okay, which is a difference of 50 seconds. All right, other than that, I am done there. So 500 plus 2,500 is 3,000, and that is the answer to part D. So part D is 3,000 meters, and it says distance, so I don't need to include the direction. Okay, stay nerdy, don't be wild.